Hi, I'm going to talk about transforms. Previously, I talked about transforms for scalar values, where I had scaling, translation, reflection, and a center parameter to choose the center of scaling. Now I'm going to talk about transforms for 3D, basically to transform vectors, so we have more channels, and we also have rotation being added. Transforms are something that we are very familiar with in any 3D environment where we can pose items. So we know we can move them, can rotate them, can scale them, something that becomes very natural to us. The idea here is to look into how to perform the same operation in nodes and apply it to any data. So not just, the transformation that items get, but, if I want to transform any data in any context by a similar operation. Of course, I'm still going to use items as my source because it's very nice to just, manipulate items in the 3D viewport and have that to control our operation. Be aware that I also use some shortcuts to make the process of resetting the transforms a bit faster. So I have Control-Shift-A to reset all of them, Control-Shift-S to reset the scale, R for rotation, and T for translation. So if I do these three one at a time, I'm going to reset the scaling, the rotation, and the translation. Or if I use Control-Shift-A, I basically reset them all in one go. So this is very useful when dealing with transforms and control objects to basically reset the values really quickly. Now I can have access to an item, position, rotation, and scaling through the item info. This one is by Denis Pontonnier, and so here I have the 3 transforms, and these will give me 9 scalar channels. The default value for position and rotation is 0, and the default for scaling, since it's a multiplicative operation, is 1. The rotation data has a tricky thing in which the data format is XYZ in respect to heading, pitch, and bank. But heading is a rotation that happens about the y-axis, and pitch is a rotation that happens about the x-axis. So between these two, there's going to be a mismatch between the data format channel and the axis of rotation. This is not a problem if I just, every node and every third-party node, etc., and even nodal motion, they all use the same data format, so there's no problem. The only issue is that if you try yourself to, let's say, filter one of the channels, and maybe you were expecting one of the channels to be about some axis, and it ends up being about some other axis. So just something that is good to know, not much of a trouble. Now let's look into an application of the compound. So here in this Suite Transform 3D item, if I go into the Form tab, I have the world spot, basically the point positions of the mesh, being transformed by the transforms of an item. This item here is called Control Root Parent. It's this red item in here. And if I just plug the delta in there, because Displacement Node Editor expects a delta, so if I just plug the delta in there, you can see that basically the pose that I give to this object is going to be mimicked by the vertices of this mesh. And so basically it means that this compound called Transform 3D matches the transformation, the operation that goes on here in layout. I'm going to reset this and put this object here a little bit away like I had before, and disconnect this. So before I open up the compound, I just want to talk a little bit about hierarchy and order of operations. So I'm going to do a little exercise in which I split the transformations that go on into an explicit hierarchy. So when I change an item, when I pose an item, there are certain things that I'm going to affect. When I pose item A, I'm going to affect its vertices if it's a mesh item, and I'm also going to affect the child items that are below it in the hierarchy of the scene. So by posing A, I'm going to change its vertices, item B, item C, item D, and also the vertices of item D. I'm not going to change their local pose. So if item B has the pose, let's say for the position 1, 1, 1, by changing the position of item A, I'm not going to change the local pose of item B, but I will change how item B looks in the viewport to the world space context. Now, the same thing we have here with this hierarchy. I'm going to express the transformations, position, rotation, and scale with a set of items. So on the top of the hierarchy, I have position or translation, and then I have the rotation split into 3 channels, heading, pitch, and bank. Last, I have scaling, and then in the end, I have the vertices being transformed by them. So why do I have rotation, heading, pitch, and bank split into 3 channels, while the translation and scaling are, I solve all 3 channels in one item? Well, that's why I call this non-commutative transforms hierarchy. So basically, this hierarchy is supposed to express the transforms that we have here when we manipulate objects in the viewport. And non-commutative means that basically their order cannot be changed, otherwise I'm going to get a different output. So when I do A plus B, I know this is going to give me the same thing as b plus a. So this is a commutative operation. The order of the operands doesn't matter. Now, if I, for example, have position p and I add 2 on the y-axis and then I add 3 on the x-axis, I'm going to arrive to this position p prime. Now, if I change the order, instead of adding 2 and then 3, I first add 3 and then 2, I'm going to arrive to the same exact position. So in this case, the order doesn't matter. So for translation, this is going to be the case. It doesn't matter which channel I apply the transformation first. So I can solve it in one go. For rotation, heading, pitch, and bank, this does not apply. So if I rotate something first on the y-axis and second on the x-axis, it's not going to be the same as if I first rotated on the x-axis and afterwards on the y-axis. So I have to split this apart, and so there's, if I change the order of these rotations, I'm going to get a different output. So this is the minimum number of items that I need to express what goes on with these 9 channels. So let's look at that in layout. I'm going to have here this translation, XYZ, rotation, pitch, heading, pitch, bank, and then lastly the scale. If I select these 5 items, so at the end I have the sphere object. If I select these 5 items, you'll see that I'll get basically the same thing as if I just posed the item itself. So each of these items will only hold values for its name. So translation will only hold values for position. Rotation, heading will only hold values for the heading, and so on. So if I select the 5, and you can see that I can rotate. Sorry about the bad display on the viewport, but nothing I can do about it. So I can rotate it, scale it, move it around. And you can see that these items perform, this hierarchy performs the same thing as if I would just, pose the object itself. The only thing that it's neat about it is that shows that I can change the order of transformations in here. Unlike, for example, for the single item, in Lightwave, we don't have, let's say, an option to choose the order of transforms. So we are sort of obligated to make those in an hierarchy of objects. So let's look at an example. I'm going to reset everything here. And let's say, for example, that I scale these on the y-axis and then I rotate. You can see that whatever I applied with the scaling is oriented by the rotation. Now let's change this in here. Let's say that I put this under the rotation bank, and I put the scale under translation, and I put the rotation heading under scale. So now if I do the same thing, I'll put everything in a flat order. So it's not supposed to be like that. Let's see. So I'm going to recover the order. So pitch under heading, bank under pitch, and the sphere under this one. Okay, so now I swapped. The scale was between the sphere and the rotation bank, and now the scale is up here. What happens, for example, if I do the same thing? If I scale this on the y-axis and now I rotate this. Oh, now it's a bit different. Whatever I scale is not oriented with the rotation. It's the other way around. Whatever I rotate is then scaled by the scaling. And so, for example, if I have a character that has an eye that is not spherical but a bit stretched, I can use this sort of trick to basically have a normal rotation conform to a stretched eye. And so you could, change the order of all sorts of things in here and see that it has a different output than the standard order. Now let me put the standard hierarchy. So let me put this back where it was. So I'm going to put the rotation under translation, the scale under rotation bank, and this one in here. I have here a compound that basically shows all possible combinations. So here we have some combinations, some possible combinations for, I'm going to treat rotation as 1. So what I have here is 6 possible combinations for the order of translation, rotation, and scaling, and also 6 possible combinations for heading, pitch, bank. And so if I come down here, I have this compound called transform 3D order. And these last 2 parameters allow me to choose what's the order of the transform. So as I change these here in the hierarchy, I can also do something similar with the index here. So it goes from 0 to 5. So let me plug this in here. I'm going to affect this by this item here called control root parent. Again, this item here. And if I plug the delta, the item starts to affect the positions of the points of the mesh. I'm going to reset the item, and well, let's see this in action. Right away, if I just rotate on one axis, you're going to see that they all look the same. But if I give another angle, you see that there's going to be a mismatch right away. So for some, since this is using, I'm using an index that goes from 0 to 36, and these are being, there's basically some distribution. So I have all 36 versions have a different order for the transforms and for for the rotation angles. And so you can see right away there's a mismatch. Some of them will have a different orientation by having one of the Euler angles being solved first, then the other. And so if I just keep getting different values in there in different channels, you're going to see that there's more difference in them. And if I, let's say, move this away from the origin, you're going to see those all these different possibilities looking even more different. Or let's say if I scale this in the X channel almost flat, so you can see what you're seeing here in the viewport. It's all the possible orders of transformations for not only scaling rotation and translation, but also for each Euler angle. So this is just an exercise, so we can see that basically through nodes, you can have these things expressed in the order that you want. I don't actually use this compound. It's just, just an exercise to make these things more visual, more obvious for you. And so I'm going to reset this. And I'm going to disconnect this here, and I'm going to talk about the order of the hierarchy and the order of evaluation. So this is the standard hierarchy order for the transform 3D that we are so familiarized with, so we are so used to. But how do we evaluate this hierarchy? Well, it's just like the hierarchy that we have here with this example for a scene. If I want to evaluate what's the final position, let's say for the vertices of item D, I don't start to transform the vertices by item A and then item B and then item C and then item D. No, I actually go the other way around. First, I transform these vertices by the item that contains them. Then I transform the vertices by the parent item, and then by the parent of the parent, and then by the parent of the parent of the parent. And so I go upstream to solve the position that the vertices have in my scene, in the world space. So the same will be true for the transforms here that were made into an hierarchy. If I want to solve this, I start with scaling. Then I go to rotation bank, then to rotation pitch, then to rotation heading, and lastly, I go to translation. And so to express these transforms in nodes, I don't use the hierarchy order. I use the inverse order, which is the order of evaluation. So we are very used to be presented with position, rotation, and scaling. And also for the angles, let me put it here in the UI with heading, pitch, and bank. So we are very used to be presented with, let's say, position, rotation, and scaling, heading, pitch, and bank. We're very used to be presented with the hierarchy order. But to solve this, to actually execute them, you have to go in the other order, in the other direction. So here is what's inside this compound, transforms 3D. First, I scale the positions, then I rotate them on the bank, so Z-axis, and then I rotate them on the pitch, so I rotate them about the X-axis, and then heading about the Y-axis, and then lastly, I add to them, so I translate them with an add node. So multiply, rotate, 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 add. Now, of course, there are some more details to this, so if I come here and I open this up, you see that I start with the center. So as we saw for scalar values, this is sort of a conjugation operation where I want to do this operation, but I want to do it in a different context. So I have my main operation, and before and after I have two inverse operations that basically change the context of where this will happen. And so I have the center value being applied in a subtract at the start and with an add at the end. And inside, beneath those two, I have the multiply for the scaling. Then I have the one rotate node each for each axis, and then I have the add node for the translation. So if I come here to this rotate, you see that I have the Z-axis, so bank, the X-axis, so pitch, and then the Y-axis, so heading. And so after all this, I also have a multiply node that will perform the reflection. And so this is basically just a Boolean operation. It either flips the values on that channel or not. And so it's a very simple operation. And then at the end of everything, I have a subtract node to perform a delta. So basically this one makes a delta between the initial position and the result of transformation. And that's what I use here many times on the displacement node editor. Now let's look into the inverse operation. So here is the operation that transforms the values, the positions. Let's look into the inverse operation. And so to do the inverse operation, I have to do two things. I have to invert the order of evaluation. So if this is the order of evaluation, I'm going to have to go the other way around. So instead of doing scaling, bank, pitch, heading, rotations, and then translation, I'm going to first do translation, then heading, pitch, bank, and then scaling. And the second thing that I have to do is I have to use the inverse operation. So instead of using an add, I'm going to use a subtract. Instead of using the inverse operation, I can instead use the inverse value. So instead of using a subtract, instead of, let's say, having x, y, z, I could have minus x minus y minus z and still have an add node. This is useful, for example, here in the rotate, where I'm not going to use the inverse operation. What I'm going to do is just I'm going to have the opposite values applied to them. And then in the end here, the scaling, I'm going to use the divide node. So I'm going to use the inverse operation for these two, and I'm going to use the inverse value for these three. So let's open up the compound. And so we can see that I have the center still being applied. So there's a subtract and an add node at the beginning and at the end. Same order for those. But then I have the reflection being done first. So reflect, instead of being done last, it's done first. And then I have the core operation. So I have the translation being done by a subtract. I have heading being done by this rotate node, pitch by this one, bank by this one. And so their axis is the inverse order. And I also have a sign node that basically makes the opposite value. And then lastly, I have a divide node. So this one is going to perform the scaling for me. So this is what is needed to perform the inverse operation. Let's look into some simple applications of the inverse operation. So for example, I can negate the transformations that the object does on itself. I can, let's say, for example, come here, change this to self. So it gives me the informations of the object itself. And if I plug here the delta, now when I move this, you see that nothing happens to the item. You can see the bounding box change, because if I disable this, you can see that, it matches the orientation that the object has, but the positions, the mesh is being transformed to perform the inverse operation of the pose that the item has. So it kind of looks like nothing was done to it, even though there were things done to it, right? So this is a way to go about it. And another thing that can be done is to change the context of the data. So we've seen also with scalars that sometimes we transform the positions, and sometimes we do the inverse transformation in a way like we are transforming the space where those positions are, not the positions themselves. So let's use this object again here. So control root, and I'm going to chain these two. So instead of using the delta, I'm going to use the result, and instead of using the delta here, I'm going to do the delta myself. So I'm going to put the world spot in here and the result in here. So now when I come here and I have, let me see, reset this, sorry, not this one, I'm going to reset the object itself. And so I'm going to change these item info to this control root parent. Right, so now it seems that nothing is happening to the object because, well, in a way, I'm transforming this item by the inverse of what this item does. And then I'm right away afterwards, I'm transforming by the item again. So these two cancel each other out. By having them in sequence, I'm doing something and then I'm doing its inverse, and so they cancel each other out. But what I can do here is I can, for example, put a clamp node. And if you, let's say, if I just put a clamp node here and I put this in the delta, the clamp node allows me to limit the position. So for example, if I come here and I put 0 on the X channel, you see that the positions are not allowed to go into negative values. And so this happens about the origin, right? And so if in this case I'm using the world spot, so if I move the object itself, well, actually, I would need to put this in before world displacement. So if I move the object itself, you can see that it hits those walls, right? It hits those walls in there. Let me put this back into local displacement. And so if I put the clamp node in between these two, let's see what I can do with that. So here, this in result, and put this -1 in here. Okay. And oh yeah, okay. So here's my item, my control item, the item I have in here. And now as I move the item, you see that it seems that it is the item that is doing that constraint. So first I change the space where these positions are, I clamp them, and then I put them back. And so it sort of looks like it's the item performing the constraint. If I connect the this here to the delta, you see that basically, the clamp part. You see that basically you can see this cubic box around the origin where the positions are being constrained. So basically, by moving this one, I make the positions hit those limits. And then by adding them again, I put them back where they were. So in a way, this is again another conjugation operation, as I've talked about in here. But in this case, it's not just like center, that is for position, but is for position, rotation, and scaling. So it's a conjugation that takes into account all the three transforms, not just one. Another application for the inverse, let me reset this, and is that I can, for example, have a fall off being controlled by it. So let's go into shading, VPR, And let me come in here. And so I have here the world spot, and I have the length of that position, the world spot position. If I connect it in here, it's something like this. Let me move the object. Let's see, where is position? Oh, no, it's rotation. Okay, so as I move the object, you can see that as the positions go away from the origin, they go into white, because, you know, from here on is values above 1, so everything looks white. And so as the positions come close to the origin, they become black because it's 0. I'm going to invert that with an invert node. And so now when they are close to the origin, they become 0. So sorry, they become 1. And when they are past the 1 distance, the distance of 1, they become black, becomes 0. Now I can change this, and I think maybe I've shown this before. I can change this with the position delta, where I have this control item. See this control item here. And instead of moving my object, I move the control item. And so I do a delta with the position, the world spot, and I plug that into the length. So now as I move this item it's like item is holding the origin, right? And as the item comes closer, these spots become white. Now, this doesn't take into account, let's say that I scale this object, rotate it. The position is just taking into account position, right? So there's not much to it. But if I do the inverse transformation, because here, if you notice, what I'm doing is a subtract. So for the transformation, this would be the same as doing the inverse transformation, where the translate or the position of the item goes into a subtract. And so if I do the full evaluation of the item pose, what I get instead is not just the position affecting the fall off, but all the other transformations. So now when I scale the item, you also see the fall off being scaled. And when I rotate the item, you also see the fall off being oriented. So this is quite nice because it means with one object, I can control some simple shapes and some simple fall offs for objects. It feels a bit more complete than just the position. So simple example of how to apply a transform to basically pose a fall off. We go back into shaded. So we've looked into the how to perform the operation and inverse operation. I also want to talk a little bit about context. So the transforms are not very useful if we, let's say, want to take into account several contexts. Here I have, the inside of a bus where, here's a radio control. And so let's say this radio control is a control item. And let's say that this control item wants to control a person getting to a location in this space. And so here I'm just focused on this context. I just want to make this person go from here to here and then turn left and then, rotate to face the seats, etc. And so I'm just focused on this context. I'm not focused where the position of this person is relative to the city where the bus is traveling on, or relative to the solar system, where the Earth rotates around the sun and spins on itself. So transforms are very useful for defined contexts. They are not very good if I want to have something that is relative to a defined context, but I also want to relate it to, let's say, the world space. So let's call the sun the scene or the world space. Of course, we know we could go into galaxies and the whole universe, etc. But let's say that the sun is our last level. It's the scene world. So the transforms are very good used within, defined context. If I start to want to have a full hierarchy evaluation with them, this is going to be very tricky, and they're not very effective for that. So let's leave that for matrices when we talk about right, up, forward, and world position, used to perform this interaction between world space and local context, etc. We can see example of this. Let's say I go here, let's say to this item, and let's say that I come here and I go into the displacement node editor, right? And let's say that instead of using the control root parent, I go into control child. And so if I come here and I put and delete this, and I put the delta here, you can see that now as I move, this is using the inverse transformation. I don't want the inverse transformation. So if I come here and I put the delta, as I move this item, you can see that this item also mimics it, but it does that in its own context. So I can move this item, into, I can move it here. I can scale it down, I can scale this parent down. I can rotate this. And it doesn't matter because it's only copying this local pose into this other context, right? So if I try to mimic the pose of this item, it's going to be a bit more tricky because I have to take in consideration not just the item itself, the position and rotation and scaling of this item, but also the position and rotation and scaling of its parent and every parent above it. So for example, if let's say that I wanted to pose this item just like this one in world space, not local, but world space. What should I have to do? If I come here, let's see. Let me just check if this is working. So yeah, I have to put the world spot in there. So okay, so now when I pose this little box, you can see that it's affected. But now if I want to pose it like it is in the world space, I would have to then add the parent item: position, rotation, and scaling. So in this case, I'm going to change this to control root parent, right? And so I put this here, put this here. Now I get something that resembles that object there. See, it's a bit tricky to select things in here. And let me put this X-ray, this item with X-ray, so I can see what goes on in there. I'm going to reset it. I'm going to reset this one. I'm going to reset my item as well. Okay, so let's see. Reset everything. All right. So you can see that the parent, the parent is being transformed. And the child is also being transformed, but it's not matching very well, is it? So what's the problem with this? What did go wrong in here? Well, if you notice the order that I applied, I first transformed by the child and then by the parent, but I forgot to put a delta. So I got subtract, vector, subtract. I have to do my own delta. So this here, put this here, put this. And so now it matches the child item perfectly, right? But while this is not too bad, it's a bit problematic if I want to do this for every item in the hierarchy. Because let's say that this is just 2 items. This is simple. But what if I have like a hierarchy like this with 4 items? Or if I have, let's say, 20 items in an hierarchy, will I have to do this transform 3D for each one of them to basically apply the world pose? Well, that's very cumbersome. So let's leave that relationship of world constraint and world relationships to matrices that we can use the right, up, the forward, and the world position. Because even in nodal motion, so if I come here, even in nodal motion, I can't set a world pose for my item. So I cannot come here and let's say choose the control child. And so I don't have a way to have position, rotation, and scale of this item to be applied in world space to this item. So I just can't apply the local pose. So these are the limitations of the transforms when applied and when we try to create world space relationships. They are better used for very defined contexts. And so, for example, here I have another example. Let's say I put this here, reset this, I'm going to reset this. And I basically come here and I have this object called cubic frame. And in its deform displacement node editor, I have the world spot being transformed by the control child, this item here. And I just basically want this little cube to be transformed. So I have this cube weight map that basically swaps that transformation with nothing at all. So if I plug this in here, you can see that I can transform this cube just like I can transform this cube in this context. So basically, it's a transfer of local transformation to a local transformation. And this is what the transforms are best for, to transfer a local transformation into another local transformation. There's a common practice in making a panel made of nulls to control things, morphs, and parameters that you want to control in the scene. So this means that I can just basically scale the parent of this control. Let's say that I want something very small to put it on a panel. And let's put this back here. Let me just scale this. And let's say that I want this to be very small, to be even maybe far away from the center, but I can still access it and manipulate it and have it control this in its own space. So even if I pose the parent and if I pose the child, whenever I manipulate that control item that is here, you can see that whatever I do to it, so now I'm moving on the Y channel, so this item moves, this mesh moves on the Y channel of its context. If I scale it on, let's say, the X channel, it's going to be scaled on the X channel of its context. And so this is what are these sorts of control parameters are better done with transforms. And so transforms are really good for that. Not if I want to create world relationships. So lastly, I just want to talk about item infos and basically referencing that doesn't require to be explicit. So we already saw that with the item info, the default input in the item is self. So this means that whenever I apply an item info, this one by Denis Pontonnier, whenever I apply this item info in a context where the node is being used, so in this case it's in nodal motion, when I have the self in here, it uses the values of the item itself. It's not going to use the values of any specific items, but the item itself. The only drawback is that you don't see anything coming out. So for example, if I move this on the x-axis, you see that here is 0, 0, 0. But this is not true because, of course, if I put this here, the position is going to be there. But if I put, let's say, a vector, constant vector with 0, 0, 0, the item goes into the origin. So it's just something that doesn't work out very well with input SPI, but this is definitely applying the position of the item itself. So it's nice to be able to reference and to get properties for the item itself without having to explicitly say what item it is. This means that you can copy paste solutions from item to item in which you have information about the item itself without having to explicitly say which item it is. Now, we can also have the same thing with the item info, with the extended item info by TrueArt. It just requires that we plug on the item index an extended spot info node item output. So this will give me the ID for my item, for the context that I'm working on. So in this case, this nodal motion is on this item. So this will output the value, the index for this item. And so after that, I have access to all these parameters that are relative to this item. So this is another way to go about it. And I really like the extended item info by TrueArt because it also gives me quickly access to the parent index, the target index. So many information, a lot of information relative to the item. And so to do the parent, I can also do not just the self. So I have here this down here. So here is the a relative referencing self, and here's another relative referencing called parent. So in which I can access information about the parent. And so there's this node by Dennis that gives me that. But I can also do it with the extended item info, in which I do the same thing as before, but I output the parent item here into the another extended item info. And so with this, I get all this information about the parent of the context I'm in. And of course, I can keep going, and just access the parent of the parent and the parent of the parent if I keep going on, I think. So I use this a lot in compounds where I don't want to, let's say, explicitly plug in all the parameters that I want to use. So here I would have to, connect all these four, and here I just put the item ID, and then internally I access the information that I want. So this makes things much easier where I can just use the item index, and then inside I do the connections that I need. So I need to do less connections, and I also end up having less parameters exposed. So these are the fundamentals of the 3D transforms and what they are best used for. And next I'm going to talk about applying them to a chain through nodal motion.